Hello and welcome to our Wednesday edition of this week's Wednesday edition of Office Hours. Tonight there is no special programming, so I am just here to answer any questions that you may have. If you don't have any, I had a couple, actually 3 questions asked out of the homework in our TRO textbook. So I'm going to start logging in and pulling that up. But as always, I will prioritize the questions in the live chat over the email ones, because you're the ones who are here and who are waiting for an answer. Hey there, Kate, and actually, you're the one who had the homework questions anyway, so that low key works out. All right, Isabel, let me see. On experiment 3, I'm not sure how to find the solubility rules. Okay, so that's gonna be so yes, Hannah, I would totally be able to do a problem like that one. I absolutely will. Okay, here. First, let me get to Isabel's question. Let's see. Here, Isabel, hang on 1 second. I'm gonna pull up. I'm gonna pull up the resources from Canvas, because I think I know what you're asking about, but I just want to double check something with the information that's been posted. Lab 3. Okay. All right, let's see. So, Isabel, here's my question for you about are you asking about the discussion question number 2 on the worksheet is what I want to know. Okay, totally. Okay, sorry, Isabel. Question number 1. Okay, let me see. Okay. So So Isabel, here's the here's the idea of what you got to do on question 1. So you make a table, right? For your data. And so I'm gonna say I'm gonna have metal 1, anion 1. I'm gonna call this metal 2, anion 2. I'm gonna call this metal 3, anion 3, and I'm gonna call this metal 4, anion 4. All right, and let's say that you get. I'm just gonna, you know what? I'm gonna go with a simplified table. I think you've got what, like a 5x4. Slot deal. I'm just going to pare this down for the sake of answering this quickly. Let's say that you get a precipitate here. That you get no reaction here, NR here, NR here. So we know with precipitation reactions that I'm going to number these. This is going to be or letter them, label them A, B, C, D. So every single point here gives you information about your anions and cations. For example, if you look at A is M1, the metal, 1, anion 1 mixing with metal 3, anion 3, and we know that these are aqueous. And because we get a precipitate, and remember, with each one of these, you swap your partners. Metal 1 pairs with anion 3. Metal 3 pairs with anion 1. And so one of these is a solid. All right, one of these is a solid. And you need to use your other data points to determine which one of those is a solid. Here, actually, I'm going to slightly alter the data in my table right here. I'm going to make the second one M3 and A1. All right, and here's the reason, because this is the type of logic that you're going to use. All right, so one of these is a solid, but you don't know which one. But you'll notice that you have M3A1 as a reactant in this thing. That means it's in the aqueous phase. So that tells you that this guy right here is aqueous. and that this right here is our solid. All right, so that you use process of elimination to figure out which ones your solid precipitate, which ones not. All right, and then you start looking for trends. For example, is you start asking questions like this. So you notice we've got an anion and a cation here. You start asking, is M1 and or A3 always insoluble? Like, is it insoluble in every single one, or is it sometimes soluble, sometimes not? Like, is it usually insoluble, but there are exceptions? You look at your data for trends, like, is there a cation that no matter what it's paired with, it's always insoluble? Maybe with an exception. Or is it always soluble across the board? And that's what it means by developing your own solubility rules. It's looking to see, is there anions or cations that are always soluble no matter what? Put them in the always soluble list. Are there anions and cations that are sometimes soluble, sometimes not soluble? If they're more soluble than insoluble, like if they're 80% soluble but then they're insoluble at 20% of the time, put them in the usually soluble category and then say what they're insoluble with. If they're usually insoluble, put them in the insoluble category and say what they're soluble with. That sort of thing. Does that make sense? And you're not graded on whether it's right or wrong. You're graded on, is it consistent with the data you recorded. So you don't have to check this with the official solubility rules thing, because I'm not going to be looking at the official solubility rules. I'm going to be looking at the data that you got from the lab simulation. Oh, dude, you are totally welcome. Absolutely welcome. Okay, Hannah, you wanted to see a problem similar to problem 9 from the review packet. Let me grab that thing really quick. All right, there's that. Let me pull up number 9. Ah, okay. I thought number 9 might be this one. Okay, so I am going to cook up a fresh problem. This is a problem that won't, that I can't just make up off the top of my head, that takes a little more effort. But I have a spreadsheet to help me. I should say I wrote a spreadsheet to help me. Let's see. There we go. Okay. Give me a second here. So I've got to cook up a new problem. Okay, let's see. How about this? Hang on, I'm doing some calculations on a scratch piece of paper just to make sure I'm gonna come up with something real. Or that. Huh. And that. Okay. Thank you for your patience. I'm almost there. I'm coming up with a new one of these from scratch. And so that would be okay. All right. So let's dive in. All right, so this is a new example. Like the exam 1 review number 9. All right. Chlorine. Hang on. So chlorine represents make sure I get this number right. 59.61 percent of the mass of a molecule with the chemical formula CzCl2. Determine the value for Z. All right. So this is a hard problem. This is a hard problem. We know what we're trying to find, right? It's right there. We're looking for, last sentence, the value for Z. Let's look at what we're given. All right. We're given the percent mass of chlorine in this molecule, 59.61%, and we're given part of the chemical formula. We know that there are 2 chlorines in it. We don't know how many carbons. All right. Now, this is becoming a theme in this class, and it is a solid theme. This is problem-solving strategy for chemistry, for physics, for all your physical science STEM courses. Whenever you're given a quantity like percent mass that has a corresponding chemical equation, sorry, not chemical equation, algebraic equation, it is worth your time to write out what that equation is, because that equation will be clutch to solving your problem. It'll be the roadmap to solving your problem. So what does percent mass equal? Well, for chlorine, it equals 2 times the mass of chlorine, right, which is, we get that from the periodic table, divided by the total mass in the molecule, which is Z times the molecular weight of carbon plus, in AMU, plus 2 times the AMU for chlorine times 100. That's the percentage. Now, if you look at what we're given, we're given percent mass for chlorine, and the atomic mass for carbon and chlorine, we can look this up on the periodic table. Carbon has an atomic mass of 12.001 AMU, and chlorine has an atomic mass of 35.45 AMU. So now that we know, because we've looked it up, the atomic mass for carbon and chlorine, there's only one variable in this equation we don't know, and that is Z, the subscript for carbon. But since that's the only unknown, we can solve for it algebraically. So, we've got, it'll take quite a lot of algebra, but we can solve it. So we have 59.61 is equal to 2 times 35.45 over Z times 12.01 plus 2 times 35.45 times 100. All right, the first thing I'm going to do, divide both sides of this equation by 100. That is going to give me 0.5961 is equal to 2 times 35.45. So that's just going to be 70.90. This is a 4, just to be explicit. Over Z times 12.01 plus 70.90. All right, now we need to solve for Z, so we need to multiply both sides of this equation by our denominator. Z times 12.01 plus 70.90. And we're doing this to both sides. So that denominator cancels. So now we have 0.5961 times 12. I'm distributing that in times Z. Plus 70.90 times 0.5961 equals 70.90. All right, let's crunch some numbers. We're just going to simplify things down. 0.5961, oops, 0.5961 times 12.01. So this is 7.159 Z plus, we got 70.90 times 0.5961, 42.2635. I'm not worrying about sig figs right here, if you're wondering, because we're just trying to find an integer value Z, right? It's going to be the subscript for carbon, so we don't need to stress about sig figs. We just need to make sure we don't round too much. I'm going to subtract 42.2635 from both sides of this equation. So we're going to get 7.159Z is equal to 28.63651. And now I'm going to divide both sides by 7.159. And my value for Z is 4.00007. So Z is 4 for this problem. It should come out to be close to an integer. It won't be exact, just like ours wasn't exact. But that is how you go about solving a problem like this. And again, it just comes down to writing out that equation for the given quantity. In this case, it was the equation for percent mass. And that was the roadmap to solving it. So definitely take that mentality with you into exam 2. It will totally pay dividends. All right. Okay. Yes. Totally. Totally, Kate. We can totally hit up all the redox stuff. Hannah, you are totally, so totally welcome. It's an excellent question to ask because it was a very challenging problem. Hopefully you can see the takeaway that like the equation, the algebraic expression will demystify any horrible problem that I can dish out. Because all the horrible problems I write are based off of those equations. It comes from those. So if you can get that, it'll be the skeleton key that unlocks door after door after door. Okay. All right. Kate, I totally have time to do all of them. The book problems and the exam caliber stuff. But which ones do you want to see first? Heck yeah. All right. So, okay, now here's my second question. Follow-up question. Do you want me to like write the problems and then just dive right in and solve them? Or do you want me to like write them up and then give you a chance to solve them and then watch me do them once you've hit the answer? Is my follow-up question. And while you think about that, I can totally start writing. I'm going to start with a... I'm totally down for either. I think if it's a type of problem that you don't know how to begin, then I should like just totally start off and work it. But if, for example, you know enough to attempt, like for example, I'm gonna ask you to balance an equation using the half reaction method, you'd probably get more out of it if you try it on your own and then see me do it. Does that make sense? And I'm totally down to work with any comfort level you have with the material. I'm gonna write, okay, let's see, I'm gonna write a decently sized problem here. Okay. Here, hang on, I've just got to pull up a scratch piece of paper to make sure. That I actually make a problem that's solvable. Okay. And, okay, so let's see. So that's being... Okay. So, balance and identify the oxidizing agent and the reducing agent. All right, so here's the thing. On the exam, I'm not going to be able to lump all of these into one problem, so they're going to be separate problems. Like one problem's going to be might have, for example, ask you to balance it. Another problem might ask you to identify the oxidizing agent. Another problem might ask you to identify the reducing agent. So these are all going to be kind of chopped up into chunks, but this one big problem kind of hits everything that you'll see, or maybe not everything you'll see on the exam, but all of this is exam caliber for the following redox: unbalanced redox reaction. This goes to and quick note, this redox reaction occurs under acidic conditions. All right, so I'm going to call this one Redox 1. I'm going to give you a chance to take a stab at it. Give me a shout. Give me a shout out whenever you'd like me to start working this problem. But in this kind of pause meantime, I'm going to start writing, for example, an acid-base problem that maybe has some stoichiometry. Also, you asked for a gas evolving reaction. I'm not going to put the gas evolving reactions on exam 2. That's the one that we're taking here on Friday, because they just make more sense to wait till exam 3, because chapter 5 will be on exam 3. So the gas evolving reactions won't be on this one, so I'm not going to do them. So I'm gonna not do a gas evolving one since they won't be on the test. But I will do an acid-base stoichiometry problem. I'm just gonna start writing it. Spot on, dude. That is 100% correct. Bromine is the oxidizing agent, and phosphorus trihydride is the reducing agent. Well done. Alrighty, and I'm going to take this. Oh, dude, you're welcome. Awesome job. I'm going to take this off the screen because I'm going to start writing out the acid-base problem that I just made. So I'm going to have this go dark temporarily. Oops. To allow for oh. Apologize for the the pause in action, Photoshop is temporarily out of commission. Not it's frozen at the moment. There we go. Okay, sweet. I messed up my part A. Part A is write a balanced chemical equation for this reaction. Part B is identifying the limiting reactant and the theoretical yield of the salt. Part C is all right. So this is the acid-base problem in its completion. When you want to see it, but I'm assuming we'll probably want to bounce back to the redox reaction first. I can also take new questions if anybody else is popped into the chat while I was writing these. Just let me know what you want to see when you want to see it. Oh! Okay, let's see. Let's find out. So I actually haven't done this problem yet. I wrote it out, made sure all the math worked out. But let's put it to the test. So we got to balance this thing first, and we are dealing with phosphoric acid, which is aqueous, plus calcium hydroxide, producing water, plus a salt. Now, the identity of that salt is going to be based on calcium cation and phosphate anion. So these are going to combine like so. All right, and now we have to balance the situation. So we have hydrogen, phosphorus, oxygen, and calcium on both sides of this equation. We have 3 hydrogen from phosphoric acid, plus 2 from calcium hydroxide, 1 phosphorus, 4 oxygen from phosphoric acid, plus 2 from calcium hydroxide and 1 calcium. Then on the product side, 3 calcium, 1 plus 8 oxygen, 2 phosphorus, and 2 hydrogen. I'm going to begin by balancing phosphorus. Which will also change our oxygen and hydrogen counts. Now phosphorus is balanced. I'm going to next balance calcium. Doing so will also affect oxygen and hydrogen. Calcium is balanced, phosphorus is balanced, oxygen looks a little strange, but hydrogen looks doable, right? 2 goes into 12 6 times. And when I balance hydrogen, I also balance oxygen in one fell swoop. So this is my balanced chemical equation. Let me clean up down here just a bit. Alright, there's my balanced chemical equation. Now I'm ready to do some stoichiometry. So we were given that we had, so we got to do a limiting reactant calculation, right? There we go. So we've got to do this calculation twice, once with phosphoric acid, and we were given 0.405 molar, that's moles of phosphoric acid per liter. We need to multiply this by our volume. Of course, we have to convert 25 milliliters to liters to get our units to properly cancel. Next, we got to convert from moles of phosphoric acid to moles of our salt, which is calcium phosphate. And this is a 2-to-1 ratio. We were asked to find the theoretical solution of the salt in grams. So we need to calculate our molecular weight here so we can convert from moles of calcium phosphate to grams. And this is going to be quite a gnarly molecular weight to calculate. Busting out my periodic table. So we've got calcium, which is 40.08. Phosphorus, which is 30 something, around 31. Yeah, 30.97. Oxygen, 16.00. But we have 3 calcium, 2 phosphorus, and 8 oxygen. This molecular weight is going to be gigantic. So we have 40.08 times 3. We have 30.97 times 2. And then 16 times 8. So this molecular weight, let's add all these together, comes out to be 310.18 grams per mole. There we go. Okay, so let's crunch these numbers. We've got 0.405 times 0.025 divided by 2 times 310.18. And 0.405, so 1.57 grams. All right, this might be our theoretical yield, but we have to do the same calculation with calcium. And I missed. That should be a 3 right there. There we go. That is our balanced chemical equation. Hang on. There we go. Oops. All right, now we've got to do calculation with calcium, which is 398. That is moles of calcium hydroxide over liters times our volume now we got to convert from liters, cancel liters. And we need to convert from moles of calcium hydroxide to moles of calcium phosphate. This ratio is a 3-to-1 ratio. Moles of calcium hydroxide cancel. And now we can convert from moles calcium phosphate to grams of calcium phosphate. 310.18. Moles cancel. Let's see, we got 0.398 times 0.025 divided by 3 times 310.18. Which is, to 3 sig figs, 1.03 grams of calcium phosphate. All right, your theoretical yield is spot on. Now let me check. I'm sure your actual yield is going to come out just fine, because we have percent yield, which is 88%, is equal to actual over theoretical, which is 0.103 times 100. So we need to multiply both sides of this equation by 1.03 grams over 100. So that 103 grams cancels 103 grams, and 100 cancels 100. So we get our actual yield is 1.03 grams times 88 over 100. Yep, and this is going to come out to be 0.91 grams of calcium phosphate. Correct on all counts. Oh, sorry about that alarm. Dude, if you are totally okay with it, I'm totally I can we totally don't have to do it. Ooh. Awesome. Okay, here. Let me write this problem up. Okay. Here it is. I baked this one while you were doing the previous one. Dude, that is totally the way to approach it. Alright, so this is a titration problem. It's a little different than the ones I presented in class, so hopefully it'll be a decent challenge. But let's see. So, 8.78 grams of a monoprotic acid analyte is titrated with 5.30 molar KOH titrant. The initial burette reading is 0.39 milliliters. The final reading is 12.67 milliliters. All right, now here's the wind up. Wait for it. What is the molecular weight of the analyte? All right, so that is the curveball that I was able to come up with off the top of my head. Okay. Oh, hey Ashley, sorry, I just saw your question. Kind of off topic. Having trouble with number 6. Okay, let me take a look. Nothing is off topic in open office hours. Let's see. Okay. Here, let me. Whoops. Let me throw up a problem that's similar, but oh yeah, totally. Similar problem, but or I should say the same problem. We're just going to do it for a different molecule. So the percent mass of carbon in carbon tetrafluoride is 13.65%. If there are 0.056 grams of carbon in a sample of let's see, of CF4, how many molecules are in the sample? Okay. Yeah, you nailed that one, dude. I was when I saw Kate, when I saw the 134.9, I was like, sig figs, but then you caught it. So yeah, straight up. Well done. Okay, Ashley, let's take a look at this guy. So here's the deal. All right. Yes, Kate, it totally was. It was not a straightforward problem, but you nailed it. All right, Ashley. So when we look at this, so here's the key to solving this problem. It really is understanding what percent mass means. All right. It means that in a sample of 100 grams, 13.65 of those grams are going to be carbon out of 100. Sorry. Out of 100 grams of CF4. But the thing about this ratio is it's correct no matter where you write it. You could also say that in a 100 gram sample of CF4, or that a 100 gram sample of CF4 will contain 13.65 0.65 grams of carbon. All right, that's what this number here means. It gives us these two ratios between the mass of carbon and the total mass of the sample. Now, if you look at that second ratio that I wrote, 100 grams of CF4 contains 13.65 grams of carbon. You'll notice that we're given the mass of carbon present, right? So if you multiply this by your mass of carbon, grams of carbon cancel. And the reason why this helps us is now the only unit is grams of CF4. And notice, we're trying to find how many molecules we're trying to find. Oops. All right, because we want to find how many molecules. The way you convert grams to molecules is first we have to convert grams of CF4 to moles. And then we can convert moles of CF4 to molecules because we know that 1 mole is 6.022 times 10 to the 23rd molecules. So all we need to do is get that molecular weight. Carbon, okay, sorry, Photoshop freaked out for a hot second there. So carbon has an atomic mass of 12.01. Fluorine is 19.00. But we've got 4 of them in this molecule. So 19 times 4 plus 12.01 gives us a ratio of 1 mole. CF4 has a mass of 88.01 grams. All right, now you'll see grams of CF4, cancel. Moles of CF4 cancel. And now we're ready to crunch our numbers. 100 divided by 13.65 times 0.056 divided by 88.01 times 6.022 times 10 to the 23rd. This gives us, let's see, we can only keep 2 sig figs because that's what our mass had. So our answer here will be 2.8 times 10 to the 21st molecules of CF4. All right, so Ashley. That is the breakdown. Dude, you are so totally welcome. All right. Actually, I was just about to write any new questions on the board, and then I remembered that I actually have a couple questions from the Tro homework that were determined over email. So this is from chapter 4, number 95, Part C. So let's see. Number 95. Part C. Determine whether each reaction is a redox reaction. For each redox reaction, identify the oxidizing and reducing agent. And this particular problem gives us lead 2 nitrate reacting with sodium sulfate to produce lead 2 sulfate plus sodium nitrate. All right, this is not balanced, but you don't need a balanced equation to determine if it's a redox reaction or identify the oxidizing or reducing agents. Now, one trick that I'm going to use here is when you're dealing with ionic compounds, you can determine the oxidation states of the ion, cation and anion individually. So we can deal with lead 2 and nitrate individually. We can deal with sodium and sulfate individually. And then we can move to the product side. So because lead is the only species in lead 2, it will have an oxidation state of +2. Now for nitrate, oxygen is going to be -2, right? Oxygen is going to be -2, and with that information, we can solve for nitrate because the oxidation state of nitrogen plus 3 times the oxidation state of oxygen will add to our total charge. Oh, I'm sorry, I meant to switch back to black there, which is -1. So nitrogen -6 equals -1. So the nitrogen in nitrate will have an oxidation state of +5. Sodium, because it's the only species in sodium cation, will have a charge of +1. For sulfate, oxygen will have a -2, right, because it's more electronegative. And now we have to write out an equation to find sulfurs. Oxidation state of sulfur plus 4 times the oxidation state of oxygen will equal our total charge, which is -2. So sulfur -8 equals -2. That means sulfur is a +6. All right. Now, let's look at the product side of this reaction. Again, we're going to do the same thing. We're going to break up our anions and cations. Because it's easier, or I find it easier in this instance to assign the oxidation states. And one thing you'll notice is we have the same 4 species on this side of the reaction that we do on this side, which means we've already assigned all these oxidation states. Lead's going to be 2, sulfur is +6, oxygen's -2, sodium is +1, nitrogen is +5, and oxygen is -2. And you'll notice that none of these oxidation states change, which means this is not a redox reaction. All right, when no oxidation states change, then reduction and oxidation have not occurred. All right, so this one is not an oxidation reaction. Second question submitted by email number 98. All right, complete and balance each combustion equation. Okay. So we haven't explicitly covered combustion, so you don't need to worry. I will not test you on this material in this way. Like, I won't ask you to predict the reactants. But I can still do this problem. So just so you know, combustion is you add oxygen and you make oxides. What do I mean? Well, an example would be part A of this problem, C4H6. We're going to add oxygen and we're going to make first carbon dioxide. There's the carbon-based oxide plus the hydrogen-based oxide, which is dihydrogen monoxide. So the elements, you take the elements in the thing that's reacting with oxygen and you're going to produce those elemental oxides. So carbon dioxide and water are the products of a hydrocarbon being combusted. We can now balance this equation. We've got carbon, hydrogen, and oxygen. On both sides of this reaction. To balance carbon, we multiply carbon dioxide by 4. So now we have 8 plus 1 oxygen's on our product side and 4 carbon. To balance hydrogen, we're going to multiply H2O by 3. So it's 8 plus 3, or 11. Now, we're in a little bit of a pickle here because we need to multiply O2 by some number so that 2 times that number equals 11, right? That'll get the oxygens to be equal. That number is 11 over 2. So this is the balanced chemical equation. However, we can't allow a fraction to remain in our balanced chemical equation. So we need to multiply both sides by the denominator of that fraction. So we will get our final answer for the balanced chemical equation will be 2 times C4H6 plus 11 molecules of O2, producing 8 molecules of carbon dioxide and 6 molecules of water. All right, so that's how you do this problem. That's part A. I'm not going to do parts B, C, or D only because if a combustion reaction were to show up on the exam, I'm not going to present it like this, where you have to predict the, excuse me, sorry for the products. I would give the products to you explicitly, so it'd just be like any other balancing problem. Okay, the last problem is a great kind of brain teaser. This is from chapter 4. Number 100. Great number. And problem 100 in chapter 4 says find the percent mass of sodium chloride in a 1.35 molar solution. And they give us the density of the solution. All right, so this is interesting. Let's think a little bit. So percent mass is equal to the grams of solute, which in this case is sodium chloride, over the grams of solution times 100, right? And molarity is equal to moles of solute over liters of solution. So really, we need to convert moles to grams. How do you do that? Molecular weight, no problem. The second thing we need to do is convert liters to grams. And how do you do that? Density. Density gives you a ratio of grams to volume. And look, we've got the density and we can calculate the molecular weight here. So this is actually a unit conversion problem. So let's get about it. 1.35 moles of sodium chloride per liter. First, let's convert moles of NaCl to grams. Sodium has an atomic mass of 22.99. Chlorine has an atomic mass of 35.45. 35. So when we add these two together, we get 58.44 grams per 1 mole. All right, now we have grams in our numerator. Next, we need to convert our denominator to grams. Now, our density First, you'll notice that our density is in milliliters. So we need to convert our liters to milliliters. So liters over milliliters. 1 milliliter is 10 to the negative third liters, and now liters cancels. Next, we want to use the density to convert from milliliters of solution to grams of solution, and our density tells us that 1 milliliter has a mass of 1.05 grams. Now milliliters cancel, and we are off to the races. Ready to crunch our numbers. So we have 1.35 times 58.44 times 10 to the negative third divided by 1.05. All right, and so this is equal to 0.07. Let's see, we can keep 36751. This is grams of NaCl over grams of solution. But we're not quite there yet. You'll recall whoa, hang on. Sorry about that. There we go. You'll recall that that the percent isn't just grams of sodium chloride over grams of solution. You got to multiply by 100. So right here, whoops. Where did that slide go? So we have 0.0751. This is grams of NaCl over grams of solution. We need to multiply this by 100 if we're going to get it to a percentage. All right, so times 100 gives us a percent mass. Sodium chloride is equal to 7.51%. All right, and that is how you do problem 100 from the chapter 4 practice homework. Oh, let's see. Rachel, I was wondering if there's a correct way to type out. Rachel, great question. So, you won't have to do subscripts. You won't have to type subscripts. The one thing for charges, so for example, I didn't put a problem like this on the exam. But let's say I asked you to enter the charge of the anion in sodium sulfate, right? And then there's a box to do it, to put that charge in. You have to hit enter. All right. Well, sulfate is an anion with a charge of -2, right? This is -2. So the way you enter a negative number is you put the sign first, and this right here is how you enter a negative answer. Because you will totally have to enter negative answers on this exam, and that is how you do it. Yes, Rachel. So that is a great question, and I don't have you type out the answer. What I would do in that case, for example, is I would so for example. Let's say that it's a precipitation reaction. You're mixing these two. The way I would phrase the question is I would ask you to enter the stoichiometric coefficient of the precipitate that forms. If no reaction occurs, enter 0. All right. So Rachel, so like for a precipitation reaction or a net ionic equation, I would phrase the question in this way: I'd give you two potential reactants, and then ask you to enter the stoichiometric coefficient of the precipitate that forms, which is going to be a whole number, right? So you'd look at the possible products, use the solubility rules to determine if there's a precipitate, and then if there is, balance the equation, and that stoichiometric coefficient for the precipitate you enter as your answer. So it's because I did this because I didn't want you guys to have to stress about like, oh, how do I format it right? Like, how do I like get all the subscripts? Basically, I've been able, using this type of strategy, to reduce a balance of chemical equation problem to you just entering a number. So hopefully that de-stresses the situation for you. That was my intent, and kind of makes your life as simple as testing in an online environment possibly can be. All right, Murat, let me see what your question is. In a lecture video a while back on solubility rules, I couldn't quite understand the relationship between OH And the usually insoluble group. Yes, absolutely. Here could be one. Let me pull up my lecture notes here. All right, let's see. Okay. So the usually insoluble ions are OH and sulfide. All right, hydroxide and sulfide. They are soluble when they're paired with the following cations: calcium, strontium, barium, or any of the always soluble. So this is what the usually insoluble means. Hydroxide and sulfide will always form a precipitate with anything unless the cation is calcium, strontium, or barium, or one of the always soluble cations. Anything else, though, automatically insoluble. That's what usually insoluble means. Yeah. So Murat, you are totally welcome. The thing you're remembering in the video is I made a comment about how technically hydroxide is slightly soluble with these three cations. And I just mentioned that because in the future in Chem 401, you're going to be delving into that. And so I didn't want it to be confusing for you when you got there. But for this class, we're just treating it as a normal soluble thing when it's paired with these. Technically, it's slightly soluble. But for Chem 400, we just get to live in a little bit of ignorance and treat it as if it's soluble. Oh, yeah. Okay, let me take a look. Okay. Question. Um, 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 Let's see. Okay. Murat, that is exactly... That helps me so much, actually. So much. Total. If you can tell me the decimal that you've calculated, I can show you how to use it to get your final answer. Oh, okay. Right. That is, I can help you. All right. So it would be incorrect to round. Yep. Totally makes sense. So, okay, so you got... Oh, hang on. Switch to black. 2.5 moles of carbon. Let me just double check something real quick. Yeah. Okay, totally. So, actually, before you even consider rounding, so you're gonna have also moles of hydrogen. I don't know what that number is, so I'm gonna call it X. And then you'll also have okay. Right. So you've got Never actually. We don't need this for this part. Okay. So here's the thing. What you've got to do. Okay. Awesome. So here's the thing. What you need to do is convert your decimal to an improper fraction. All right, because as of right now, we have C 2.5, H 4O 1. 2.5 is 2 1/2, right? If you were to make it a fraction. Then as an improper fraction, this would be 5 halves. So this would be C 5 over 2 H 4 O 1. And then what you do is get rid of your fraction by multiplying each one of these by 2, by that denominator. So this 2 cancels this 2, and now you've got your correct ratio. No, it wouldn't make it the molecular formula. Because the thing is, we're not a factor like that you get by comparing the empirical weight to the molecular weight. But we weren't given a molecular weight here, so we actually can't determine the molecular formula. This is just simply getting the simplest whole number ratio between all your elements in the molecule. Murat, it is absolutely my pleasure. I'm so glad I could help. Ah. Rin, great question. Sorry, I stepped out of my office to use the restroom for a moment. I actually earlier in office hours did the same type of problem, just with a different molecule. I'm gonna see if I can find it. There we go. Wow, first blood. Okay, so this is essentially the exact same problem, but just with a different molecule, just a different molecule, different numbers. Okay, here we go. Oh wait, no. Sorry, this is not this. This is not that problem. Sorry, hang on. Oh, no worries. I did it earlier, but I've got it. I've got it somewhere. Let me see. That was not. I thought I found the problem, but I hadn't. Okay, that means it was earlier than this. No, not that. Okay, let me just go back. Right, that's the first one. Here we go. Okay, here it is. All right, so here we go. Chlorine represents 59.61% of the mass of a molecule. The chemical formula CzCl2. Determine the value for Z. All right, so basically, here, and actually, it'll make more sense if I actually write this out in real time rather than flashing a slide of previous work. So the key to solving this thing is, so we've been given the percent mass, right? And anytime you're given a value that that correlates to an algebraic expression, it is in your best interest to write that expression out. So the percent mass of chlorine is equal to 2 times the mass of chlorine in AMU, right? We pull that from the periodic table, divided by Z times the mass of carbon in AMU, because there's Z carbon atoms here, plus 2 times chlorine's AMU again, times 100. That's the equation for percent mass. And here's the thing. We can get the AMU for carbon and the AMU for chlorine all from the periodic table. Right, all of these come from the periodic table. And, whoops, we're given the mass percent in the problem. That means the only unknown in this equation is z. So, and I actually, earlier in the video, I work it out step by step. Let me see if I can scrub back to it. Okay, yeah. So, So I start this problem about 20 minutes into the live stream, and then I hit up every algebraic step. So if you want to see the step-by-step breakdown of, because this is kind of like the big picture layout for how you would solve it, and then if you want to see the like brass tacks, all the algebraic manipulations, this problem starts 20 minutes in. Oh, no worries, dude. Alrighty, well that is going to it is 10:01. That's gonna do us for our Wednesday office hours live stream. Thanks everybody for coming out. It was a great office hours, lots of great questions. I hope you all have a good weekend, and I will catch you on Monday. Later.